This is Stanford Engineering's The Future of Everything, and I'm your host, Russ Altman. If you're enjoying the show, please share it with somebody you care about, somebody who you think would benefit knowing about the future of everything. Personal recommendations are one of the best ways to spread news about the show. Today, Aaron Lindenberg will tell us that there's a fundamental trade-off in atomic processes between their speed, the energy it takes to make them go, and the reliability of their output. It's the future of ultrafast materials. Before we get started, a reminder that we have the future in a minute. At the end of this conversation, I'll ask Aaron some quick questions. He'll give me some quick answers. It'll be the future in a minute. Before we get started, another reminder to please share the show with somebody you care about who would benefit from knowing about the future of everything. Well, materials are literally what makes the world around us. In particular, electronics, optics, batteries, power. These are key materials that fuel our technology that we all have become totally dependent on. A key idea is that these materials are often what we call non-equilibrium or dynamic. That is to say, at the atomic level, these materials change in response to processes. So, for example, a proton, a ray of light, hits a material in a solar cell, and it turns that dynamically into electricity. That's distinguished from equilibrium materials where they're resistant to change, and actually they don't change when you give them inputs, and sometimes that's a positive as well. But for most of electronics, we're looking at non-equilibrium or dynamic materials. And our ability to understand these materials has become revolutionized by our ability to measure them and look at them on ultra-fast timescales. Well, Aaron Lindenberg is a professor of material science and photon science at Stanford University, and he studies materials at the highest speeds and in the smallest scales in order to understand how they work. Aaron will tell us how these measurement technologies are enabling new understanding that promises to increase our ability to create better and better materials. So, Aaron, to start out, how did you decide to work in this area of material science, which we'll get to?
Yeah, actually, my background is in physics, and actually, one of sometimes you learn, you have experiences where they kind of imprint on your brain and they kind of change how you think about things. So for me, actually, in grad school, I remember really clearly actually learning about a problem in biology, actually. So this is not material science, but this was kind of what got me on this path. And it was a problem about how hemoglobin and myoglobin work and how they carry oxygen through the human body. And so this was a problem where people used these amazing techniques called X-ray diffraction to kind of make images of where the atoms were in this kind of amazingly complicated crystal. So Max Perutz was the guy who kind of did this and won the Nobel Prize back in the 1960s, I think, for this. And when he made this,
I met Max before he died as an undergraduate, and it was a huge thrill. Yeah.
So the story, at least as I learned it, was that when he made this picture of this kind of molecule, it was so complicated, and the structure was so unbelievably complex that there was no way that the oxygen atom could kind of migrate through this complex structure and bind to this central heme group. And so on the one hand, they had this idea that if you could understand the structure of something, then you could, this would allow you to understand how it functions and all kinds of things like that. And rather, in this case, it created a mystery. And what people eventually realized was that this molecule was dynamic. It was opening up in this amazingly complex way to allow the oxygen to come in. So that was kind of how I got really excited, not just about material science, but also about kind of the dynamics of how materials move at the atomic scale.
Great. That's a great origin story. And as somebody who studies biology, it's great to know that we can spawn great physics, great material sciences work. So for people who don't think about material science all the time, can you just give us like a little thumbnail sketch of what is the goals of material science, and particularly from your perspective and the problems that you're working on, kind of getting us to what are the big questions that like motivate your lab?
Mm-hmm. Yeah. I would say it's a question. There's a lot of fundamental science that goes into it, just asking really fundamental questions. And then also there are a lot of kind of really technologically relevant applied questions that come into it. At its basis, we're interested as a material scientist in understanding how materials work, in understanding where the atoms are, where the electrons are, and then at this microscopic level, how this amazing complexity leads to functionality. So if you want to make a device out of out of a material, right, you have to understand how electrons and ions flow through these structures. And if you can do this, then you can start to kind of harness these kind of fundamental processes and, make devices like solar cells or batteries, things
Right.
like that.
So, that's great. And I know that part of what's exciting in your field right now is kind of an unbelievable ability to measure and see atoms like at the atomic level. You described this challenge of understanding hemoglobin, and it sounds like the technology has really advanced. And so, can you paint a picture for like the kind of power tools that you now have at your disposal that enable super detailed understanding of what's going on in material?
Yeah, right. A lot of it actually, in some sense, connects to this original hemoglobin problem, right? So this was the way that Max made these measurements. In the end, Max Perutz made these measurements was by using X-ray scattering approaches. So they took an X-ray beam, which is essentially a beam of light with very, very short wavelength comparable to the spacing between atoms, and essentially bounced it off of a crystal of these things. And by measuring the diffraction pattern, which is essentially an interference effect, the beams of light kind of scatter off of each of the individual atoms, and create interference effects in the same way that you see interference effects when you look at light reflecting off of a puddle on the ground, or when you look at light reflecting off of a DVD or something like that. So essentially, by making these types of measurements, you could kind of work backwards and reconstruct where the individual atoms were in the structure. And then more recently, and this is where I kind of started out as a grad student, really exciting new tools have been developed. Some of them just up the road from Stanford at the SLAC National Accelerator Lab. And these are tools which allow one to do this type of experiment. But not just measure the structure, but measure the dynamics of this process, how it's changing on amazingly fast timescales. And sometimes people have the sense that these very fast timescales are things that are maybe not that important to our everyday lives, but really materials, when you zoom in on them, the atoms are moving on amazingly fast timescales, femtosecond timescales.
So this is great. So give us a sense, because I know a little bit about this, and it gets hard to think about things being so fast. So can you lay the landscape for somebody who doesn't think about this all the time, about exactly how fast we're doing it, maybe in comparison to other phenomena that they might be roughly familiar with?
Yeah. One way it's oftentimes described is that, so I mentioned 1 femtosecond, so that's 10 to the minus 15 seconds. And so, one way to think about it is that 1 femtosecond is to 1 second, as 1 second is to something like the age of the universe.
Okay.
So that's just one way to kind of, appreciate how short this time scale is. It's really beyond the human mind to kind of comprehend it in some sense. But nonetheless, materials are moving on these types of timescales, and so it's a challenge. For the because in the same way that if you take a picture of something, and the object is moving very, very, very fast, it will be blurred out, and you'll get a blurry image. People developed flash photography as a way to kind of get around this, right? And so this kind of illuminates the object for a very short amount of time and allows you to take a snapshot of this process. That's kind of what we're doing in a lot of these experiments. We're kind of taking snapshots of these structures as they evolve on these very short timescales.
So let's talk about the snapshots and the actual experiments that you do. So you get a piece of material that you find interesting, I guess, right? Is this a tabletop measurement device, or is this a huge device? And how do you and your students and your other research collaborators, how do these experiments actually get done? And what are the readouts that you then analyze?
There's a lot of different kind of approaches to this. Some of them are really tabletop type experiments where you can, a single student can really get to work and in a day, make a snapshot of these types of things. when you start to push the length scales, when you start to really want to zoom in at the atomic scale, we tend to often make use of the larger scale facilities. So I mentioned the SLAC National Accelerator Laboratory. This is a multiple kilometer linear accelerator that was originally built for kind of particle physics type experiments and has been kind of repurposed over the last few decades. And now it's essentially a source that allows one to create bursts of X-rays to do exactly this type of flash photography.
And if I understand, you're not just taking so-called still photographs, you're also making movies. So tell us how we make the movies, but more importantly, like what can we learn from a movie that you might not get from a still photo?
Yep. Yeah. So the way essentially you make a movie in the same way that when you make a movie in that that you watch at the movie theater, right? Essentially, it's a whole bunch of still photos put together in a way that's sequenced such that when you kind of run them from one to the next, you turn this into a real movie that captures some dynamical process.
And who are the actors in these movies? Are you looking at like an individual carbon or oxygen molecule or atom, or are you looking at the electrons? I mean, how fine a grain are these photos?
Yeah,
Excuse the extended analogy.
Sometimes we're looking at this might be a crystal, like in the example of hemoglobin. This was many copies, something like 10 to the 23 copies of these kind of individual molecules, all kind of locked together to form an overall kind of periodic crystal that you could see with your own eyes. But more and more people are kind of pushing to do these measurements at the nanoscale, where you might imagine, for example, a single nanocrystal, a single quantum dot in the focus of this beam, and essentially taking a snapshot at the nanoscale of this evolving object.
Great. Okay, so we have this gives us, I think, a really good, it took some time, but it's important to have this groundwork on what your capabilities are. And so I guess the next question is, what are the kinds of questions you ask? I know I'm intrigued because you've made statements about we're looking at the fundamental speed limits for some kind of electronic or optical devices. That sounds important to me. So maybe let's start. Tell me about speed limits.
Right. Yeah, this is something that has motivated us for a long time. And it's actually, again, one of these problems that is really interesting from a fundamental perspective. And also, as you mentioned, has a lot of really important kind of problems in technology, right? So, from a fundamental perspective, this comes down to questions like how fast can you switch a material? How fast can we oftentimes encode a 0 or a 1 in a device by the position of an atom within the unit cell. And so you could ask questions like, how fast can you really switch that structure, right? This defines, in the end, speed limits that define how fast a computer can operate or how fast a device can function. And it turns out there's been a lot of kind of really interesting and amazing kind of theoretical developments as well over the last couple of years. Essentially, people trying to take ideas that in high school and kind of early in college, you learn thermodynamics, which is the kind of a way of thinking about processes at equilibrium. And so it's only very recently that people have been able to kind of extend those ideas to non-equilibrium processes where there's dissipation, where energy is lost in these processes. And so these types of snapshot experiments that we apply can let us get a handle on these things, visualize these processes. And then the next important step, and this is again where we're really excited, is kind of thinking about controlling these processes, right? So if you can see these processes in interesting ways, then you can start to think about, well, how can I engineer this process? Is there a way for me to, control how I switch a material from a 0 to a 1 state in a way that minimizes the energy cost or maximizes the speed by which it occurs?
So I don't know if this is a fair question, but with respect to speed limits of things like computers, are we at a position where you can tell me that we are pushing up against it and that the last 40, 50 years of speed ups that you and I have experienced just as a human in our electronic devices, is that era coming to an end, or do you see plenty of headway so that, yeah, of course there are physical limits, but we have not gotten anywhere close to them? What's the general sense?
It's quite interesting. We're many orders of magnitude away in both the speed limits and in the energy costs.
Okay.
Right. So a typical computer might operate at gigahertz like frequencies. Right. That's 10 to the 9 kind of operations per second. Right. And there are processes that I was talking about. Essentially that are related to kind of really fundamental processes and how you encode information in an information storage device, where you could push this to picoseconds, 10 to the minus 12 instead of 10, instead of 10 to the minus 9.
So that's
And
times faster right
1,000
there.
times faster. Yeah. And then energy, I mentioned, is also, in some sense, even more important, right?
Yes.
In this age of AI and so on, right? We all
Server
know
farms, yes.
Server farms, right, are equivalent of a nuclear reactor, and in terms of energy costs, right? And so you can ask again this question of how much energy do you really need to make a single operation, like a single transistor? Imagine zooming into your computer, right, and saying, well, how much energy do I really need to kind of switch that transistor, right? And it turns out, again, in this case, we are many orders of magnitude away from the kind of fundamental limits. It turns out people actually, at least for an equilibrium process, kind of understand pretty well what that kind of fundamental limit is. It's something called the Landauer limit, and it essentially it kind of encodes the kind of fundamental amount of energy you need to kind of erase or a one, or take a one and transition it into a zero. And it turns out that the energy costs that we're at, you can put some numbers on these things, actually, right? People are pushing a lot, talking about something called the attojoule frontier, which is where you're trying to.
Yes, atto is ATTO, right? ATTO, and it's even smaller than pico.
Even smaller than pico, even smaller than femto, right? This is 10 to the minus 18 joules. That's one attojoule, right?
Right.
And so people are there's a lot of excitement about making devices that operate with energy costs associated with that type of dissipation.
Yes.
And it turns out that the fundamental limits defined by the Landauer limit are something like 10 to the minus 21 joules, right? So This is a zeptojoule, actually. There's a word for even that.
Wow. Okay. So if I'm hearing you correctly, this is super good news, because it means that these server farms, they might not. I mean, it's not tomorrow. I understand that this is basic discovery, and there's always time to translate it into devices and capabilities for engineers. But we have plenty of headroom. Again, just as you were talking about speed, we also have energy efficiency opportunities that indicate we should not give up on very low energy versions of the kinds of things that right now we have big batteries or big server farms. That there's a lot of potential.
That's right. And actually, one other interesting point, it turns out these things are interconnected. These ideas of speed and energy costs are really kind of interlinked in really interesting ways. So one of the reasons why we're kind of, in terms of these energy costs, not at these kind of fundamental limits, it turns out, is because computers are intrinsically dynamical things, like we're talking about. They're non-equilibrium processes. Computers are not quasi-static in the way that we kind of think about thermodynamics as kind of applied on an equilibrium process. And so when you try to make processes happen dynamically over very fast timescales, it turns out you need to put more and more energy into them to drive. And the faster you want to go, the more energy you need to dissipate. And so there's an intrinsic kind of trade-off between these things that is really interesting.
I see. So should we think of it as a speed energy trade-off? Is that basically the trade-off that's happening?
Exactly right. You sometimes call it, there's a kind of a speed kind of time uncertainty principle in some sense that kind of encodes.
Okay. So that's good, though, because once that trade-off, once we have it all under control, there are things that we don't need to be fast, but we need to be efficient, and there are other things like our phone calls or whatever that we need to be fast, but perhaps we would be willing to pay a price in efficiency.
Exactly, that's right. And then another thing that comes up often is reliability, right? When you store information, you want that. You store one or something. Yes. You want that to be stable. So when you save a photo of your kids and you want to go back and look at it 10 years from now, it better be there, right?
It would be nice,
right? And so this aspect of reliability also is encoded in this kind of trade-off. You can make things less reliable, but then maybe switch and operate more fast, or you can make them more reliable, but maybe then there are more energy costs associated with them.
This is The Future of Everything with Russ Altman. We'll have more with Aaron Lindenberg next. Welcome back to The Future of Everything. I'm Russ Altman, and I'm speaking with Aaron Lindenberg from Stanford University. In the first segment, we got a little tutorial on our ability to measure the atomic properties of materials with amazing technologies that give us the scale in both space and time that makes very fast processes look slow because the measurements are so fast. In this segment, I'm going to ask Aaron about simple things like solar cells, randomness, and how AI is helping him in his work. Don't forget, at the end of the segment, we'll have The Future in a Minute, where I'll ask some quick questions and get some quick answers. So, Aaron, in this section, I want to start out with things that people are pretty familiar with: batteries, solar cells. What are they to you as you look at them as a material science, and what are the opportunities kind of to understand them better and then to make them better?
Right. Yeah. So, think about, let's take the solar cell as an example, right? So this is a device which takes photons, light from the sun, and turns it into electricity, right, at a fundamental level, right? But if you zoom in, if you think about, what's really happening at the atomic scale, and imagine that you have, perfect resolution to see these processes as they unfold, right? Then what you actually see is something where, maybe a single photon of light is absorbed in the material, silicon or whatever that material is, right? It creates an excited electron. That electron starts to move through the material. It's scattering and bouncing off of atoms within the crystal structure.
And excited means it has a lot of energy, right? It has absorbed all that energy from the light, and now it is not going to just sit there quietly.
That's right. Yeah. And so in the end, of course, if you want this device to work, you have to take that energy, right? That energy, you've converted that energy from light into electronic, right? But now it has to make its way out, and there has to be a current or a voltage that is developed, right? Across two leads to actually power some device, right? And so it turns out that if you want to understand the ultimate efficiencies of this process, right? Like, how efficient can you make a solar cell? The processes that come in here, the time scales and the length scales are amazingly short in time and amazingly small in length scale, right? So on picosecond time scales, this electronic energy, some of that energy is lost as the this kind of hot electron kind of relaxes.
Right.
If you want to kind of capture that energy, then you need to find a way to make that device. You need to find a way to extract that energy on these very short time scales.
Yeah, before it basically just turns into heat.
Exactly. And once it's turned into heat, now suddenly this is a form of energy that is hard to use for performing work in the end, right, from a thermodynamics perspective. So in the end, understanding, being able to see these processes allows one to, number one, think about find new materials, work in kind of feedback loops where you can kind of think about a whole bunch of different material systems where you've tuned the properties of the system in different ways, and kind of run these kind of operando like experiments where you kind of see the device as it operates. You measure these kind of processes at the atomic scale, and you measure maybe simultaneously the operation of the solar cell, how much current is actually flowing through the device, and you can kind of start to correlate these things and use this as kind of a design principle to kind of discover new materials, to optimize the performance of the material and so on.
Yes. It does remind me of your very first founding example where the oxygen was trying to get through that protein. And now you've drawn a very similar picture in my head where there's this electron and you're trying to kind of channel it into, with all its other fellow electrons, basically into a stream of electrons that are heading towards presumably some kind of positive charge to create the current. And I can imagine that different materials would be either better or worse at kind of allowing you to channel those electrons. So you've written about randomness. How does that? This whole thing seems kind of random, but I think you mean random in a much more kind of theoretically manageable way. So tell me about the role of the randomness in your work.
Right. So actually, even taking that same example we just talked about, the solar cell, uh, when that photon gets absorbed in the material and creates electronic excitations, you also, it turns out, drive reconstruction of the lattice. The atoms move around in complicated
Ah,
ways. So this is, again, some materials. This is kind of a really important process, and people think even that this dynamical motion of the atoms protects and
uh huh.
makes the material more efficient in interesting ways. And so this is a process that involves kind of the way we think about it in material science is it's overcoming an energy barrier. So there's some kind of energy. It's just like when you're kind of climbing a mountain, right? And there's a mountain in front of
Right.
you. You kind of have to kind of try to make your way up, and it takes a lot of work, of course, to kind of overcome that barrier. In the same way, at the atomic scale, there are energy costs that are associated with overcoming barriers and switching materials in that way. And this process, it turns out, has a really interesting element of randomness. Sometimes we use the word stochasticity to
Yep.
describe this. And the way we think about this is that the material is kind of you're maybe trying to take energy from the sun and kind of push this material over this barrier, right? But it's kind of fluctuating and it's making attempts trying to get over the barrier, but falling back, and so it turns out that at the atomic scale, at the nanoscale, these types of fluctuations become really, really important, right? In the same way that if you zoom in on a material
Right.
at
Right.
room temperature, right? If you can actually see what the atoms are doing, they're not just sitting there steady; they're fluctuating and
Yes.
vibrating in really kind of complex, random ways. And so that randomness and understanding how that plays a role in the efficiency is a really important process, and it's a really challenging problem as well, because when we make these movies like I was describing, right, where we kind of make snapshots of many of these processes and put them together, oftentimes we kind of do these measurements in kind of an averaging mode, where you might like run the experiment many, many
Right.
times and
Right.
take many different snapshots and put them together. And the assumption that we make when we do these experiments, when we do those experiments, is that kind of the process is kind of always following the same trajectory every time.
Yes.
And this
Yes.
turns out to be a bad approximation when you zoom in at the nanoscale. These materials are fluctuating, and each time you kind of run a chemical reaction, it might do something different each time. And so, how to kind of capture that and deal with that is a really central challenge.
Yeah, I find that to be very intuitive because you see these pictures that people take of rivers where they leave the camera on for a long time and the river looks like this beautifully smooth like flow of water, but anybody who's actually watched a river in detail sees that there's all of these eddies and there's all these other motions, and what I'm hearing you say is you need to capture those. And now we can see why we're going back to these ultra fast movies and pictures that you're able to take, because I'm gathering that it actually is within range to get these kinds of photos, so to speak, to
Yeah.
understand that randomness and how you can kind of harness it, or at least distinguish between materials whose randomness seems to be more favorable for the application at hand versus ones that are actually fighting it too much.
Right. The river example is a really good one, actually, because it also gives you, it brings us to this idea. As we often use the word heterogeneity. So materials are heterogeneous in the sense that if you look at different parts of the material, different parts look different, right?
Yep.
There's defects, there are all kinds of complexities, and you can't kind of just assume that everything is doing the same thing and everything. When you make these kinds of averages, you lose information about the dynamics in the same way that a river has this amazing complexity.
So in the last couple of minutes, I just wanted to ask you about AI. I also know from your work that your group does use AI, and I'm wondering, like, what has the impact been? Is it a significant impact, or is it somewhat peripheral to the work? And what are the opportunities? Are you bullish?
Yeah, I think it's a really exciting time, and there's no question that there are ways in which AI is going to play a really central role. I talked about these diffraction experiments, for example, where you bounce a beam of X-rays off of material, right? This creates an amazingly complex pattern on a detector that we measure, right? And these images are kind of coming in at very high rates. It's a massive data problem just to kind of analyze these images, right? And so people are thinking a lot about how to use AI to kind of provide kind of real-time feedback on an experiment, right? Where you might, as you're running the experiment, get some feedback which allows you to change some parameter, as you kind of develop a new material or as you kind of build a new device. So there's a lot of excitement there. Another interesting example is in this idea of control of a process that I talked about previously, right? But we're thinking a lot about ways in which we can, for example, we're trying to measure some device as it operates. We apply some voltage waveform, some voltage switch that switches the material, right? And you can think of lots of different kind of waveforms. And the question is, what is the optimal one that minimizes the energy cost, like we were talking about before?
I see.
And so this is, again, a problem where you're searching through this massive phase space of possibilities. It's totally unobvious what the optimal kind of protocol is, and so AI, we think, can help us to kind of solve these types of engineering problems.
Yeah, that strikes me as a good match, because the optimal waveform, as you say, might be an incredibly weird looking like waveform, right? It might not be a sine or a cosine. It's just some crazy, and that's the kind of thing that AI can patiently try different options and tune and say, okay, here's the one. It looks random, but this is the one that might work. And it complements human capabilities where we're not always the best at thinking of crazy shapes.
Yep, that's exactly right.
Fantastic. Well, that's great, and that's exciting. And before we end our conversation, I wanted to move to our segment that we call The Future in a Minute. And this is just where I ask you kind of 5 straightforward questions, and you give me kind of short answers. And I'm wondering if you're ready for The Future in a Minute.
Let's begin.
Okay, let's do it. First question. What is one thing that gives you the most hope about the future?
I think for me, a lot of it is about the really exciting opportunities kind of at the boundaries of fundamental and applied science. There's really exciting opportunities that can make our world a better place. And then maybe another quick answer to that, if I'm allowed, is my experience kind of working with young people on these projects. These are kind of amazingly collaborative projects, and so seeing them in action also gives me a lot of hope for the future.
What's one thing you want people to walk away from this episode remembering?
Probably the importance of non-equilibrium science, the importance of really seeing things at the atomic scale and how they dynamically evolve, and how this is a really important problem that can affect our everyday lives.
Aside from money, what is one thing that you need for your research to succeed?
There's probably a few things. One is being stubborn, kind of being really having the courage to kind of take on really challenging problems, and not giving up in the face of experiments always fail, and being able to push through these. And then the other really important aspect of doing science is about kind of the collaborative nature of it, right? And all the experiments that I talked about here involved a huge number of people, and would have been impossible without this kind of collaborative atmosphere. That,
if all goes well, what does the future look like?
I think an opportunity that I would be excited about, if all goes well, is people thinking about problems in a scientific perspective. So if we could, if science, and actually when I say that, I don't mean thinking about things in a cold, logical kind of way all the time, but kind of approaching problems and thinking creatively about them. If people could approach this kind of way of thinking, then I think I would be optimistic about the future.
If you were starting over again and you needed to get your degree or certification in a different discipline, what would that be?
There's a few things that come to mind. One, maybe neuroscience. I've always been excited about the brain and how this works and the complexity and actually the dynamics that underlies
Pretty
it.
complicated material.
Pretty complicated material. And then another example might be music. Actually, music is also something that's really central to my life. And actually, I think a lot about the parallels between doing science and playing in a band. There's kind of amazing collaborative types of work. You have to work with other people in ways to creatively make progress on something.
Thanks to Aaron Lindenberg. That was the future of ultrafast materials. Thank you for listening to the show. Your ratings and reviews help inform the community and get people on board with the future of everything. So if you haven't yet, please rate the podcast. We'd love to get a 5.0 if we deserve it. We don't want too much grade inflation. Or write a review telling us what we've done well and maybe where we could improve. We read every comment that you make, and we care deeply about those. Thanks so much. Thanks for tuning into this episode. Don't forget, we have more than 300 episodes in our back catalog, so you can really spend quite a bit of time pondering the future of anything. You can connect with me on many social media, including LinkedIn, Threads, Blue Sky, and Mastodon, where I'm at RB Altman or at Russ B. Altman. You can also follow Stanford School of Engineering at Stanford School of Engineering, or more easily at Stanford ENG.